Hi, this is ProofPilot. As I have mentioned before in my videos, I live in Iran, and these past few months we had a lot going on. There were protests and war. Let's just leave it there. If you want to learn some quantum mechanics and its mathematical tool, and at the same time know what happened to Iranians during war, this is your video. I hope you enjoy it. Though it wasn't an ordinary day, you might think. We were all expecting it. Of course, after what happened on January 8th and 9th and President Trump's stance. I was in the shower when the first bomb hit Tehran. Then there was just chaos and terror of what might come. We all headed back home, but fun things happened still. I heard one of the professors after the first bomb just closed the window and continued to teach. We were planning to play basketball on the campus until security kicked us out. That's the Iranian spirit. So after we all headed home and the supreme leader of Iran was declared dead and some celebrated it, I knew we were going to be in this for more than a while, so I decided to study quantum mechanics. So I opened the Griffith book, Introduction to Quantum Mechanics, and Israel and US were bombing outside. Well, the book starts with Schrödinger's equation, but where this equation comes from still is not that clear for me. But the best I can do is that it's based on experiments and some inspiration from classical mechanics. Well, this equation has a psi function which gives information about the particle. But what are those experiments that motivated this equation to be constructed? They are named photoelectric effect and the double slit experiments. I think there are a lot of videos on that on YouTube. You can check them out, but in brief, they tell us that energy or light is quantized and waves can act like particles and particles can act like waves. And these two equations came out of E equal to h omega and P equal to hk. And in classical physics, a wave function looked like this. Now, if you differentiate this with respect to time and x, you get some interesting results. For the wave, we have this equation, and by differentiating it, we get this one. For wave differentiating with respect to x, we get this equation. This suggests the operator substitution that we can replace, which makes operators an important player in the game. Now in classical mechanics, we have this equation, E equals to the potential plus momentum squared over 2m, which is the kinetic energy. Replace E and P with operators that I just said, and we get the Schrödinger's equation. There are other explanations of how this differential equation can be derived, but let's just stop here. Unlike classical mechanics, which given an initial state and an equation can predict the position and velocity at all time, the Schrödinger's equation just tells you the probability of the presence of the function at an interval of time. Well, this might seem very strange, but this is the core of quantum mechanics. But what happens to all those quantities that we care about in classical mechanics? Well, here it comes the probability theory with a not bad of a solution. Imagine that you have a dice and someone asks you, what is the number on the rolled dice, and tells you to roll it. Well, you cannot give an absolute answer. It can vary from 1 to 6, but someone may say 3.5, and that person absolutely is a statistician. I mean, the rolled dice cannot show 3.5, but you expect it to be 3.5 by this formula. The same thing applies to quantum mechanics, just note that we deal with integrals instead of sum, and psi squared is the probability density function. So the probability of a particle being in an interval AB is the integral of psi squared, and the expected value of the position of the particle is the integral of psi squared times x. The velocity is defined as the derivative of expected value of x with respect to time, and the momentum is just the... It was right at this moment that 2 blocks away from my house was bombed multiple times. Fortunately, I duct taped our home's windows and they were not broken, but other houses were. Everyone was in the streets to see what happened, unlike other countries where they go into bunkers. And to be honest, some people were scared, but again, in the next 5 minutes, everything seemed normal again. Apparently, there was a drone factory nearby which was targeted. As I was saying, the momentum is a bit odd because when you don't know where the particle is and you just have a probability of where it is, then you cannot define a velocity as you know in classical mechanics. So we say that momentum is the derivative of the expected value with respect to time times m. Well, I talked about how the integral of psi squared is the probability of the particle's presence in that interval. So as we have in probability theory, this integral with integration bounds from -infinity to infinity should be equal to 1. After all, the sum of all probabilities should be equal to 1. But wait, let's look at the Schrödinger's equation. If psi is a solution, then so is a psi, and the total probability condition will not be satisfied. The solution is we take the psi and determine the constant, and we accept this as the representative of psi group. But still, there is one problem left. If we normalize this psi, how do we know that it's gonna stay normalized for the rest of time? The interesting fact is that this integral does not depend on time. The procedure will bore you, so I'm going to skip it. Just use the Schrödinger's equation. I'm sure you can obtain it. The bombing continues, schools closed, factories closed, and everything is on hold. Oh, and I forgot to mention that from the first day of the war, there has been a digital blackout. Again. We still don't have access to internet as I'm writing the script of this video. Yes, there are some strange ways to connect, which is impressive from Iranian people. It's like the whole country has a master's degree in security and network. But they are expensive and not affordable. I once paid $8 to connect to fill an application form. And believe me, that's a lot of money for just 1 gigabyte of internet in Iran. Anyway, let's go back to quantum mechanics. You may think that this monstrous equation is unsolvable, but there is some hope. First, let's simplify matters as you do in every hard problem. So let's just assume that the psi function is separable, meaning it can be written as two functions psi of x and t of t, and solve the equation. So we start from the time-dependent Schrödinger equation. H represents the Hamiltonian, which is equal to this formula. Now let's assume that the wave function has this form. It means that it can be separated, and just note that psi of x only depends on x and t of t only depends on t. Now let's just substitute this into the Schrödinger's equation and obtain this form. And now let's divide both sides by psi of x and t of t. As you can see, the left side only depends on t and the right side only depends on x. Since these are equal for all x and t, both must be equal to a constant. Let's call that constant E and solve these two differential equations. As you can see, we have transformed a partial differential equation into two ordinary differential equations. The first one is if you have past differential equations. The second one needs a bit of more information about v of x. So here's the answer for the first one, and for the second one we're just gonna skip it for now. And the solutions will give us psi of n and e of n. You may now wonder that not all of the solutions are separable, and this solution is not complete. This part needs a lot more mathematical background, which I'm not an expert in. But apparently the set of all three solutions form a basis in Hilbert space, which is the space of all valid psi functions in the sum of probability formula, and the total solution will be obtained by this formula. And interestingly enough, Cn squared decides the probability of the particle with energy En. It's like how much of your psi function is in the answer. I will clarify on this part in the linear algebra part. The matter of solving differential equations and obtaining different psi's for different potentials are technicalities which I'm going to skip. They use some cool techniques, but maybe in another video. It's day 22 and we are celebrating Iranians' New Year Nowruz. Most of the people that live in Tehran are spending their holiday at Shomal, which is the north of Iran, including me. We try to keep our spirit about war and hope that the right side of the war wins. At the end of these 10 days, Trump announces he's gonna blow some of the power plants, and this one really frightens us. We hope that it doesn't. Let's get back to quantum mechanics, and it's time for linear algebra to kick in. Remember how I said that the momentum is the derivative of the position expectancy times m? Well, if you calculate that, you get these results. Another way to write that is, and we enter the territory of operators, as I mentioned before. Momentum is one of them, so is the position. Momentum acts like this, as you can see. Position is just like a multiplication. Now let's define an inner product, which you probably are familiar with from linear algebra. And by the way, we are still in Hilbert space. Now we call an operator Hermitian if it has this property. All observables are Hermitian. Now you must ask, what is the point of this? We are in quantum mechanics. If you do some measurement, it's going to give you some random result due to its probabilistic nature, but not all of them give random results. Hermitians don't. I'll leave this one for your curiosity to find out. So if they're gonna give the same results, then a Hermitian operator action on a particle is going to give a constant Q, like this. You may recognize this form. We call these states the determinate states. And remember how I told you that we construct the solution of Schrödinger's equation with this formula? Well, the psi n are the eigenfunctions from this formula, and En are the eigenvalues. This is the formal language of quantum mechanics. Well, I'm genuinely tired of quantum mechanics because of how it's so messy in 3 dimensions. It has these weird formulas that you must compute each time. Not really my thing. But there was one strange night in this period, April 7th. We were all expecting to go back to Stone Ages. All of us ready at midnight. Everyone was awake, everyone was showered, everyone got a haircut. It was like a New Year's Eve, but luckily nothing happened. We are on a ceasefire. They don't fight, they are not at peace. My friend said it's like a war situationship. But anyway, I hope we all pass this alive. Thank you for watching.